Before talking about force, it helps to notice something odd. Almost everyone uses the word with confidence, and almost no one pauses to ask what it actually means in physics. Force sounds obvious. You push something, it moves. You stop pushing, it stops. That story feels complete and familiar. Because of that, force often becomes one of the first ideas people stop questioning. It turns into something you memorize formulas for instead of something you understand. That's where people start to get confused. Force is often introduced early, quickly, and with symbols that seem to explain more than they do. Arrows appear on diagrams, equations show up on the board, and before long, force feels like a technical word for effort, something strong things have and weak things lack. But physics means something far more specific by it. Consider something simple. You can push against a solid wall with all your strength, and nothing moves. No visible result at all. At the same time, an extremely small force acting on an object in deep space can slowly change its entire path across millions of kilometers. The difference isn't strength, it's how motion is allowed to change. That observation already points in the right direction. In physics, force is not defined by how hard something feels. It's defined by how motion responds. If an object speeds up, slows down, turns, or is held in place when it would otherwise move, force is involved. If none of those things happen, force may still be present, but balanced by something else. This leads to a statement that sounds wrong at first and then becomes unavoidable. Motion does not require force. Change in motion does. An object moving in a straight line at constant speed does not need anything acting on it to keep going. It only needs something acting on it to alter what it's already doing. This idea took a long time to accept, largely because everyday life hides it from us. Air resistance, friction, and contact are everywhere, so motion almost always fades unless something keeps interfering. Physics removes those effects and asks how motion behaves when nothing interferes. Seen this way, gravity takes on a different role. Gravity doesn't make objects move. Objects already move. Gravity changes how they move. It bends paths, redirects motion, and holds systems together without supplying motion itself. The same is true for friction, tension, and pressure. They don't exist to create motion. They exist to limit, redirect, or prevent changes that would otherwise occur. Thinking about force this way removes much of the mystery. Force stops being an invisible push and becomes a description of how motion is restricted. As that understanding settles in, a more fundamental question naturally appears, one that goes beyond pushes and pulls and begins to explain why motion in the universe follows rules at all. From this point forward, force can be described with precision, without leaning on imagery or habit. In physics, force belongs to the description of motion as it unfolds in time. It appears only when motion does not remain the same. That connection is exact, measurable, and repeatable. At the most fundamental level used in physics, force corresponds to how momentum changes over time. Momentum combines two things: how much matter an object has and how it moves. When that combined quantity changes, force enters the description. When it does not change, motion continues exactly as it is. This definition matters because it strips force of intention. Force does not decide. It does not push with purpose. It does not aim. It simply expresses how interactions alter motion as time progresses. This also explains why force never belongs to a single object in isolation. There is no force sitting inside an object waiting to act. Force arises only through interaction. A hand and a box, Earth and the moon, a charged particle and an electric field. Without interaction, there is nothing to describe and no force to speak of. That idea removes a large amount of confusion. Objects do not carry force. They participate in interactions, and force describes how those interactions affect motion. Because force arises from interaction, it always depends on context. The same object can experience different forces depending on what it interacts with and how those interactions occur. A book resting on a table interacts with earth and with the table. Motion remains unchanged because those influences counter one another. The forces exist, yet momentum does not change. Force does not promise motion. It describes the tendency for motion to change unless something counters it. This leads directly to how multiple forces act at the same time. Motion responds to the total influence of all interactions present. An object does not choose which interaction to obey. It follows the combined result of all of them. That combined result determines how momentum evolves. This is why forces can be represented with arrows and added together. Each arrow represents how one interaction contributes to change in motion. Adding them produces the total effect. Nothing further intervenes. Motion follows that result. Gravity fits naturally into this description. Gravity does not exist to make objects fall by default. It alters how objects move when mass is present. A planet orbiting a star continues moving forward due to its existing motion. Gravity continually redirects that motion inward, changing direction without needing to change speed much. The orbit forms because direction changes continuously. Direction matters just as much as speed. A constant speed with changing direction counts as ongoing change in motion. That alone requires force. This explains why an object moving in a circle experiences force even when its speed remains constant. The same logic applies to tension in a rope. Tension does not exist to freeze objects in place. It redirects motion that would otherwise occur. Pressure in a fluid guides how motion spreads through contact. Friction alters motion by transferring it into many smaller motions among atoms, redistributing energy. Force never acts as an independent cause. It describes how interactions reshape motion from moment to moment. This view also explains why force and energy are closely related without being the same thing. When an interaction changes motion through distance, energy transfers. When motion changes direction, energy may shift form while totals remain accounted for. Force handles the local description of motion change. Energy tracks the global accounting. Both describe the same physical events from different perspectives. One focuses on evolution over time, the other focuses on conservation. Another important point follows from this. Because force depends on interaction, it always appears in pairs. When one object influences another, the interaction involves both. Each responds according to its properties, and motion adjusts accordingly. This pairing is not philosophical. It is built into how interactions are defined. That pairing does not mean forces cancel. It means interactions involve mutual influence. Motion changes according to how those influences act together within the system. This is also why force has direction. Direction indicates how motion changes, not where something wants to go. The direction of a force shows how momentum changes, not the direction of motion itself. An object may move one way while the force points another way entirely. This distinction matters. It explains why forces can redirect motion without speeding objects up or slowing them down. It also explains why force diagrams work even when motion looks complicated. At this stage, force stands as a precise statement. Force describes how interactions control the evolution of motion over time. Nothing more is required. This description holds across mechanics, fluid motion, electromagnetism, and beyond. The same concept applies whether the interaction is contact, gravitational influence, electrical interaction, or something deeper. That universality is why force remains useful. It provides a language that applies broadly without assigning meaning or purpose to physical behavior. Force also sets limits. It tells you what motion cannot do under given interactions. It tells you which changes are allowed and which are excluded. That is where real understanding forms, knowing what motion is restricted from doing under specific conditions. With this framework, talking about force no longer relies on metaphor. It relies on relationships, change, and time. It can be explained clearly, applied consistently, and extended without contradiction. From here, forces lead naturally into fields because many interactions do not require contact. Fields describe how interactions extend through space. Force describes how motion responds locally to those interactions. The two fit together without conflict, and from there, the rest of physics connects smoothly. Momentum explains motion, force explains change, energy accounts for what is possible, time orders the sequence. Nothing extra is needed. Motion follows rules because interactions leave no alternative. When force is understood as the way interactions govern how motion changes over time, its reach extends far beyond mechanics exercises or diagrams filled with arrows. It starts to shape how physical explanation itself works. One immediate consequence appears in how causes are treated. Force does not answer the question of why motion exists. Motion simply occurs. Objects move because motion is allowed. Force enters only when relationships between objects place limits on how that motion can evolve. In that sense, force does not generate motion, it restricts it. That reversal carries weight. Everyday language treats force as something active, something that makes things happen. Supervise assigns it a narrower role. Motion comes first. Force defines how motion responds when interactions are present. This ties force directly to momentum, energy, and time. Momentum measures motion itself. Force measures how that motion changes as time passes. Energy tracks what changes are permitted overall. Time orders the sequence. Each concept plays a distinct role, yet none stands alone. Together, they form a single framework rather than a list of separate ideas. Another consequence follows from interaction. Because force arises only through interaction, it never belongs to an object by itself. It always depends on what else is included in the description. The same object may appear force-free in one situation and force-driven in another, depending entirely on which relationships are taken into account. That dependence does not weaken explanation, it strengthens it. Physics does not describe isolated things, it describes systems. Force belongs to the system, not to the object. Motion changes because relationships exist, not because objects carry invisible influences within them. From this perspective, rest and motion stop feeling like opposites. Both correspond to unchanged momentum. A book resting on a table and a spacecraft moving through empty space share a common feature. Motion remains constant. Forces may be present, yet balance keeps momentum from changing. What matters is not presence or absence, but balance. This reframes how stability is understood. Stability does not require absence of force. It requires forces that counter one another. The stillness of a bridge, the orbit of a planet, the shape of a rotating system, all arise from interaction, not from lack of influence. Another surprising result emerges when force is examined across different areas of physics. Contact forces, gravity, electrical influence, and magnetism feel unrelated in daily experience. One involves touch, another weight, another invisible attraction. In physics, all serve the same role. Each describes how interaction alters motion. The laws differ because interactions differ, not because force itself changes meaning. Whether motion bends due to mass, charge, contact, or structure, force always answers the same question: how does motion respond at this moment? This shared role explains why force laws can appear varied yet consistent. The mathematical form changes, but the function remains identical. Force remains the link between interaction and motion change. At the same time, another important consequence appears. Force does not always provide the most efficient description. In many systems, tracking forces directly becomes complicated, while energy accounting remains simple. Pendulums, roller coasters, orbital motion, each can be described through forces, yet energy often gives faster insight. That preference does not replace force, it assigns it a role. Force handles local evolution. Energy handles global constraints. One explains how motion changes step by step. The other explains what motion may or may not do overall. Together they describe the same physical events from different angles. Force also plays a role in prediction. Knowing the interactions acting within a system allows motion to be projected forward in time. This predictive power made force central in classical physics. Given interactions and initial motion, later motion follows. Yet force does not guarantee simple outcomes. Initial conditions matter. The same interactions can lead to different results depending on starting position and motion. In complex systems, fluids, turbulence, many body systems, forces remain precise while outcomes vary widely. Rules remain exact, results remain sensitive. That sensitivity reveals something important about physical laws. They do not dictate outcomes, they restrict them. They narrow what motion may do without prescribing a single result. This leads naturally to meaning rather than mechanism. Physical laws act as boundaries. They do not instruct the universe how to behave, they tell it what it cannot do. Force laws belong to that category. Motion may unfold in many ways, but only certain changes remain allowed. This asks why understanding in physics often comes from limits. Knowing that momentum cannot change without interaction. Knowing that direction cannot alter without force. These are not observations drawn from habit. They are restrictions that hold universally. Force contributes directly to that style of understanding. It defines which changes are excluded under given interactions. That exclusion gives structure to explanation. Another consequence appears when force is connected to fields. Many interactions operate through space without contact. Fields describe how influence exists throughout space. Force describes how motion responds at a particular location. The two concepts complement each other without overlap. Nothing travels from one object to another to push or pull. The field describes a relationship embedded in space. Motion responds according to that relationship. Force names that response. Here, force acts as a bridge between structure and motion. Fields describe influence. Force describes response. At this stage, force no longer appears as a building block of reality. It appears as a translator. It translates interaction into motion change. It translates structure into dynamics. It translates relationships into evolution through time. That role explains why force remains powerful at human scales while giving way to other descriptions at deeper levels. In relativity, gravity appears through geometry rather than force. In quantum theory, interactions appear through probabilities and exchanges. Yet the role force filled, linking interaction to motion change, remains present under new language. Force occupies a specific place in understanding. It may not describe the deepest layer of reality, yet it provides one of the most effective ways to connect motion, interaction, and time. What force ultimately tells us reaches beyond mechanics. It tells us that motion is not free to evolve arbitrarily. Relationships matter. Interaction shapes change. Motion unfolds within boundaries set by how things relate to one another. Force expresses that boundary. It shows how motion responds when relationships exist. It gives form to change without adding intention or purpose. At this point, force can be placed where it belongs within the structure of physics. Force provides a reliable way to connect physical situations that appear unrelated on the surface. Falling objects, rotating systems, flowing fluids, structural support, collisions, orbital motion. Each of these situations reduces to the same underlying task, describing how interaction influences motion over time. Force serves that task with precision. That precision carries practical weight. Engineers rely on it to calculate load and motion. Scientists rely on it to test predictions. Technology relies on it to function consistently. Wherever classical physics applies, force behaves in a dependable way. There are facts about force that hold across every tested situation within its range. Momentum changes only through interaction. Force arises from relationships between objects or between objects and fields. Multiple interactions combine to determine how motion evolves. Junction matters as much as speed. These statements remain valid across experiments and applications. There are also clear limits. At extremely high speeds, describing gravity through force loses effectiveness and geometry takes over. At extremely small scales, interaction takes discrete forms that force alone cannot capture.
For humans, the entire universe could not function without light. We see and understand things because of light. Without it, our eyes cannot see objects. In fact, we humans couldn't survive without the sun's light. Light plays a crucial role in understanding the structure and properties of everything from atoms to the universe. This light raises many questions for humanity. Since ancient times, we've been trying to understand what light is. Light acts like a messenger of information. When it encounters an object, it reflects off that object, carrying information from it, then enters our eyes. Within a millionth of a second, our brain processes this information and helps us understand what we are seeing. Even though light is a messenger of information, it is itself invisible. That's why space appears so dark. We can only see the existence of light when it encounters an object. We see rays of sunlight because they pass through dust or gases. We already know that light travels at the incredible speed of around 300,000 kilometers and doesn't require any medium to travel. This is the maximum speed of our universe. It is a very special and unique property of light. Nothing else can travel at this speed. However, one of the greatest physicists of the 19th century, who worked on electricity and magnetism, predicted through his equations that light is just a part of radiation. Along with light, all radiation travels at the same speed. This radiation is called electromagnetic radiation, or electromagnetic waves, electric and magnetic force. Every charged particle in our universe has an electric field. An electric field is simply a distribution of force, or lines of force. Electric field lines are the simplest way to understand an electric field. First introduced by the father of electricity, Michael Faraday, electrons have a negative charge, so they have an electric field, while protons have a positive charge and also have an electric field. However, the fields differ depending on the charge. For a positive point charge, the electric field lines radiate outward, while for negatively charged, the electric field lines radiate inward. Simply put, the electric field originates at a positive charge and terminates at a negative charge. In the case of an isolated positive point charge, the electric field line starts at the charge and extends to infinity. For an isolated negative point charge, the electric field lines start at infinity and end at the negative charge. So this field exists around the charge at all times, even if there are no other charged particles nearby. Although the range of an electric field may be infinite, the strength decreases with distance, meaning the field is stronger near the charge. The electric field is responsible for electric force, where, like same charges repel each other and opposite charges attract. The field is always active. When two opposite charges come close together, the Electric field of the positive charge links with the electric field of the negative charge. When two positive charges come close together due to their similar outward fields, they repel each other. Magnetic forces were first observed in natural magnets. Similar to electric fields, magnets also have a field called a magnetic field. A magnet always has two poles, a north pole and a south pole. Magnetic field lines always start at the north pole and end at the south pole of the magnet. Like electric charge is similar. Magnetic poles repel each other, while opposite poles attract. The main difference between electric and magnetic fields is that in nature, negative and positive charges can occur independently of one another, whereas magnets always have two opposite poles. We have never found independent magnetic poles in nature with only north pole or only south pole. Even if a magnet is cut into two pieces, each piece becomes a new magnet with both a north and south pole. No matter how many times we cut it, the pieces always have opposite poles. Electromagnetic force. Our universe operates with four fundamental forces: the strong force, the weak force, gravitational force, and electromagnetic force. Electromagnetic force is a combination of electric force and magnetic force. But why do we combine them? Why can't they be separate forces? The story of electromagnetism begins with the invention of the battery. In 1800, Alessandro Volta invented the battery, a device that pushes electrons from one place to another. This movement of electrons is known as electricity. An electron is a charged particle, so when a charged particle moves, it creates electricity. In 1820, Danish physicist Hans Christian Oversted conducted a famous experiment. He placed a compass near a current-carrying wire. Naturally, a compass needle points in the direction of north and south pole, direction of Earth. But when he placed near the current-carrying wire, the needle deflected from its original direction. This demonstrated that the movement of charges produces magnetic effects, which is why the compass needle was deflected. However, a stationary charge, no matter how large, has no effect on a magnetic needle. A charge must be moving in order to create a magnetic field. When charged particles move in a straight line, they produce magnetic fields around them. For charges moving in the opposite direction, the magnetic field will also be opposite. This can be easily explained by the right-hand rule. Point your right-hand thumb along the flow of current. Then curl your fingers as if wrapping around the wire. The direction your fingers point is the direction of the magnetic field created by the current. The 19th century was an incredible period for new inventions. At that time, the only source of electricity was the battery. But the demand for electricity was enormous. Scientists had to find a way to produce electricity other than by using batteries. Faraday worked on this problem. He asked himself if electricity could produce magnetism. Why couldn't magnetism produce electricity? After years of work, he succeeded in 1831. When a coil of wire is connected to a current meter and a magnet is moved inside the coil, the needle on the meter deflects. When a magnet moves forward, electrons start moving. When the magnet moves backward, electrons start moving in the opposite direction. A changing magnetic field causes electrons to move in different directions. If we place a light bulb, we can see that the bulb starts glowing because the moving electrons create electricity. This indicates that a changing magnetic field produces a changing electric field. With this discovery, we later created generators, which are used to produce electricity. Generators are simple. When we rotate, a magnet changes in its direction, produce electricity. Thus, a charge will produce a magnetic field, but only if it's moving. A magnetic field will produce a current, but only if it's changing. A moving charge produces a magnetic field. But what happens if the moving charge suddenly changes direction? This phenomenon was explained very well by one of the greatest physicist mathematicians, origin of electromagnetic waves. Faraday's ideas on electricity and magnetism were put into mathematical form by physicist James Clerk Maxwell. He formulated 4 beautiful equations on electricity and magnetism. For easy understanding, let's review these formulas in simple terms. His first equation is a bow, UT electricity. It states that electric charges, whether positive or negative, create an electric field. The second equation is about magnetism. All magnets have 2 poles. The magnetic field starts at one pole and ends at the other. Therefore, magnetic charges cancel each other out. This means there are no magnets that exist with only one pole. Magnets always have 2 poles. And the magnetic charges cancel each other out. The third equation explains that a charge in motion produces a magnetic field, and a changing magnetic field induces a changing electric field. These first 3 equations are relatively straightforward, and we already have some understanding of them. Now we move on to the next step. What happens when a charge accelerates? Acceleration means an object changes its speed or direction. A charged particle can vibrate, which means it continuously changes direction. and vibration implies acceleration. Let's observe the vibration in slow motion. First, the charge moves upward, creating a clockwise magnetic field around the charge. Then the charge moves downward, creating a counterclockwise magnetic field. This happens very quickly. So the magnetic field around the charge also changes rapidly. Now it becomes clear. We already know that changing magnetic fields can induce changing electric fields. So as the charge vibrates, the changing electric field induces a changing magnetic field, and the changing magnetic field induces a changing electric field. This process repeats continuously, propagating through space. The electric and magnetic fields work together to push each other along. This field conversion is called electromagnetic waves. At any point, the electric and magnetic fields are perpendicular to one another and to the direction of propagation. This is the fourth equation of Maxwell. Electromagnetic waves are produced whenever a charge is in accelerated motion. These waves don't require any medium to travel. They can propagate through a vacuum. If the charge stops vibrating, new electromagnetic waves won't be produced. But the waves already created will continue to spread. From his equation, Maxwell calculated that electromagnetic waves propagate through space at a constant speed of 300,000 kilometers and never slow down or stop. He realized the speed is very close to something familiar to us, the speed of light. This led him to conclude that light itself is an electromagnetic wave. However, the existence of electromagnetic waves was only a mathematical prediction by Maxwell. But in 1888, German physicist Heinrich Hertz produced electromagnetic waves in his laboratory and proved that their speed is 300,000 kilometers is in a vacuum. This was the first experimental proof of electromagnetic waves. We know that accelerating charges produce electromagnetic waves, but why do charged particles accelerate? And how can light and electromagnetic waves be the same? To answer this, we need to understand the basic nature of waves. Structure of electromagnet. IC wave. Like ocean waves, electromagnetic waves have crests and troughs. The crest is the highest point of the wave, and the trough is the lowest point. The center between the lowest and highest points is called the mean position. The distance from the mean position to the crest or trough is called the amplitude. This is the height of the wave. An amplitude is measured in meters. The distance between two consecutive crests or troughs is called the wavelength, which is also measured in meters. Its symbol is lambda. A crest and a trough together make up one wave cycle. If one wave cycle passes through a point in 1 second, the time period is 1 second or 1 hertz. If 10 wave cycles pass through a given point in 1 second, then it's 10 hertz, which is called the frequency. The number of wave cycles passing a particular point in 1 second is its frequency. Consider 3 electromagnetic waves traveling at the same speed. Since the speed of these 3 waves is the same, the number of wave cycles crossing a point per second would vary, e.g., if the first wave cycle is long, fewer wave cycles will pass per second compared to the other 2 waves. So the first wave has a low frequency, while the third wave has a higher frequency. This means that a longer wavelength has a lower frequency, and a shorter wavelength has a higher frequency. The frequency of a wave is inversely proportional to its wavelength. But how do electromagnetic waves have different wavelengths and frequencies? We know T. Hat electromagnetic waves are produced by the acceleration of charged particles. But not all charges accelerate or vibrate at the same rate. If a charge vibrates slightly, it produces lower frequency electromagnetic waves. If a charge accelerates rapidly, it produces higher frequency electromagnetic waves. So the intensity of vibration determines the frequency of an electromagnetic wave. The basic principle of electromagnetic waves is that their speed in a vacuum is equal to their wavelength, multiplied by their frequency. If we multiply any given electromagnetic wave's wavelength and frequency, we get the speed of light. The speed of light never changes. If we want to find the wavelength of an electromagnetic wave with a frequency of 900,000 Zs, we just need to use this formula. So wavelength equals the speed of light divided by the frequency. In this case, we would find that the wavelength is 330 meters. The wavelength and frequency are directly related to each other. All electromagnetic waves carry energy, and the amount of energy depends on their frequency and amplitude, the higher. The frequency, more energy, the lower the frequency, the less energy. Electromagnetic waves come in different wavelengths, frequencies, and energies, so we classify them into different categories. Classification of electromagnetic waves. We already know that the distance between 2 consecutive crests is called the wavelength. The longest electromagnetic waves are 100,000 kilometers long with a frequency. Why, as low as 3 hertz. Electromagnetic waves can theoretically have wavelengths as long as 1 billion km. But such wavelengths are undetectable because their frequency is less than 1 hertz. Even at a speed of 300,000 kilometers, such a wave wouldn't compete 1 cycle per second, so the energy becomes undetectable. The shortest electromagnetic waves have a wavelength of 10⁻12 meters, or even smaller, with a frequency of 10 to the power of 24 or more. Based on wavelength and frequency, we categorize electromagnetic waves into different groups: radio waves, microwaves, infrared, visible light, ultraviolet, X-rays, and gamma rays. The most extreme waves are gamma rays, which have extremely high frequency and energy. Depending on their frequency, their energy varies. The human eye can detect only a certain range of electromagnetic waves between wavelengths of 380 nanometers and 760 nanometers, which we call visible light. Visible light, since visible light is familiar to us, we will start with this group. Unlike other groups, it's very special because we see things and understand the universe through visible light. To understand visible light, we need to look into Bohr's model of the atom. Electrons orbit the nucleus in different energy levels. And these energy levels vary by atom. Energy is measured in electron volts for a hydrogen atom. The first shell's electron has minus 13.6 eV. The second shell has minus 3.4. The third shell minus 1.5, and so on. The energy of electrons and atoms is quantized, meaning that the energy of the first shell is fixed at minus 13.6 eV. It cannot be minus 13.7 or minus 13.5. This is the same for all hydrogen atoms in the universe. In nature, electrons orbit in their ground state, but when they gain energy, they jump to a higher energy level. E.g., imagine an electron in a hydrogen atom gains some energy, and it jumps from the second orbit to the third orbit. The electron in the second orbit has minus 3.4 eV, and in the third orbit it has minus 1.5 eV. This means the electron gained 1.9 eV of energy. That's why it jumped from the second to the third orbit. As we have seen before, electrons always prefer to be in the lowest available orbit, so they eventually return to a lower orbit. Return means it undergoes acceleration and its velocity changes. When a charge is accelerated, it emits electromagnetic radiation. We know that the wavelength, frequency, and energy of electromagnetic waves depend on the rate of acceleration or vibration of the charge. When an electron moves from the third orbit back to the second orbit, it emits an electromagnetic wave with an energy of 1.9 eV. This energy packet is called a photon. Electromagnetic waves and photons are the same. Particle nature, electromagnetic waves, or photons. There is a formula for converting energy into wavelength. And in this case, we find that the electromagnetic wave has a wavelength of 654 nanometers. The visible light range starts from a wavelength of 760 nanometers to 380 nanometers, which we call the visible light spectrum. A wavelength of 654 nanometers corresponds to red light. In the visible light spectrum, red light has the longest wavelength, while violet has the shortest wavelength. The energy range for visible light from red to violet is 1.63 eV to 3.26 eV. Any energy released within this range is visible light. If an electron in a hydrogen atom jumps from the fourth orbit to the second orbit, it emits electromagnetic waves with an energy of 2.55 eV. Corresponding to a wavelength of 488 nanometers, which is green. Thus, we have red light, green light, blue light, violet light, and many others. They differ only in wavelength, frequency, or energy. Perception of color, that something happens in our minds. White light consists of all color wavelengths. But when it strikes an object, most of the color wavelengths are absorbed by the object's atoms, leaving only red light to be emitted. That's why red objects appear red. A wavelength of 654 nanometers is emitted by just one hydrogen atom at a time. But the sun contains 10 to the power of 57 hydrogen atoms. Due to the extreme pressure of the sun's inner core, atoms heat up and gain varying amounts of energy, causing electrons to jump between different energy levels. Depending on the distance of their jumps, they emit electromagnetic waves of different wavelengths. Electromagnetic waves are not only emitted by the sun's inner atoms. In the sun's plasma, countless free electrons vibrate randomly, also emitting electromagnetic waves of various wavelengths. Plasma refers to the part of the sun where unpaired ions and nuclei exist. Moreover, there are trillions of stars in the universe, all emitting electromagnetic radiation. All high-temperature objects emit visible light, electromagnetic waves. Humans also emit electromagnetic radiation, but not in the visible light range, infrared radiation. Infrared radiation lies just beyond red visible light, with wavelengths between 760 nanometers and 1 million nanometers, or 1 millimeter. When an object is not quite hot enough to radiate visible light, it emits most of its energy in the infrared range. Infrared radiation has an energy range of 0.0012 eV to 1.65 eV, e.g., if a molecule releases 1 eV of energy, its wavelength is 1,240 nanometers, which falls in the infrared range. Infrared radiation is produced by the vibration and collisions of molecules within an object. You might wonder how neutral molecules, which have no charge, can produce electromagnetic waves. Take the carbon dioxide molecule as an example. It consists of 1 carbon atom and 2 oxygen atoms. Carbon has 6 electrons, and oxygen has 8 electrons. So the molecule has 22 protons and 22 electrons, making it electrically neutral. However, the electron distribution is uneven. The atom with more electrons pulls the atom with fewer electrons. So in this case, the oxygen atom pulls the carbon atom more strongly, creating an electrical imbalance between atoms. The atom with more electrons becomes a negative pole, while the atom with fewer electrons becomes a positive pole, even though the overall molecule is neutral. It has 2 electrical poles and is called a dipole molecule. When the charge oscillates, it produces electromagnetic waves. During molecular vibration, these charge poles stretch or vibrate, producing electromagnetic waves. The frequency of electromagnetic waves depends on the frequency of molecular vibration or rotation. Each molecule has a different range of vibration modes. For instance, when carbon dioxide absorbs the right amount of energy for vibration, it produces a wavelength of around 1,000 nanometers. Thus, carbon dioxide can absorb or emit electromagnetic waves with a wavelength of around 1,000 nanometers. Heat causes molecules to vibrate, since heat is the primary source of infrared radiation. Any object with the temperature emits infrared radiation. Even objects we think of as cold, such as ice, emit infrared radiation. In fact, an object with a temperature above absolute zero emits radiation. Absolute zero temperature is minus 273 degrees Celsius, and achieving absolute zero is physically impossible. Our average body temperature is 37 degrees Celsius, so we constantly emit electromagnetic waves with wavelengths of around 10,000 nanometers, which are infrared. As we can see, the wavelength of electromagnetic waves depends on how hot objects are. As heat decreases, the intensity of electromagnetic radiation decreases, causing the wavelength to increase. Hotter objects release shorter wavelengths because their atoms vibrate more rapidly, while cooler objects release longer wavelengths. Since infrared lies beyond the visible light spectrum, we cannot see it, but some animals, such as snakes and frogs, can detect. Even though we cannot see infrared radiation, we can feel it as heat. However, we have managed to create infrared cameras that help us see infrared radiation, which is useful in many industries. At night, when there is no visible light, all objects on Earth become dark, but they still emit infrared radiation. With the help of infrared cameras, we can see objects in the dark. Microwaves have wavelengths longer than infrared waves, ranging between 1 millimeter and 1 meter with corresponding energy ranges from 0.0012 to 0.000012. EV. We are most familiar with microwaves because they cook food rapidly. Every food contains water molecules, and these water molecules can absorb specific ranges of EM waves. In a microwave oven, there is a vacuum chamber with magnets and electrodes called a magnetron, which produces a specific range of electromagnetic waves. When these waves encounter water molecules, they cause the molecules to vibrate and rotate. These vibrations and the resulting friction between the molecules generate heat, cooking the food quickly. In household microwave ovens, we typically use electromagnetic waves with wavelengths of 122 millimeters. Microwaves are reflected by metals but can easily pass through plastic or glass, which is why we use plastic or glass containers to cook food in the microwave. Microwaves are also used for long distance and satellite communications, radar systems for spacecraft navigation, and measuring the speed of vehicles. Radio waves. In the electromagnetic spectrum, radio waves have the longest wavelengths and the lowest frequencies. Their wavelengths range from 1 meter to 100,000 kilometers, with frequencies ranging from 300 MHz to 3 Hz. 1 MHz is equal to 1 million Hz. At 300 MHz, the wavelength is 1 meter. Due to their long wavelengths, radio waves are considered the safest form of non-ionizing radiation. Since their wavelengths are long and their frequencies low, they have low energy. The energy of radio waves ranges from 0.00000012 eV to 10^-14 eV. Non-ionizing radiation doesn't have enough energy to remove tightly bound electrons from atoms, so it doesn't cause damage to the cellular structure of our bodies. However, long-term exposure to radio waves with higher frequencies can increase body temperature. Radio waves are produced by charged particles when they accelerate. We artificially produce radio waves more than any other type of electromagnetic wave by moving electrons back and forth in a device called an antenna. Naturally, these waves are produced by lightning and astronomical objects such as galaxies and nebulas. We have seen that electromagnetic waves with longer wavelengths than visible light have lower frequencies and energies, making them non-ionizing radiation. Thus, they are safe for use in everyday life. Wavelengths from 700 nanometers to 100,000 kilometers are considered non-ionized radiation, N. Unionized radiation cannot break the atoms and molecules in living organisms. However, electromagnetic waves with wavelengths shorter than visible light are extremely high in frequency and energy, making them very harmful. Ultraviolet radiation makes up about 10% of the total electromagnetic radiation from the sun. UV wavelengths range from 400 nanometers to 10 nanometers, with energy levels between 3.1 and 12 eV. Like visible light, ultraviolet radiation is emitted by excited electrons. For example, consider the Bohr's model of a hydrogen atom. The electron in the first orbit has minus 13.6 eV, and in the second orbit it has minus 3.4 eV. If the electron gains enough energy, it can jump from the first to the second orbit. When it returns to the first orbit, it emits 10.2 eV of energy, which corresponds to a wavelength of 122 nanometers, since ultraviolet waves fall between 410 nanometers in wavelength and between 3.1 and 12 eV of energy. An electron returning from the second to the first orbit in a hydrogen atom releases ultraviolet radiation. Similar to hydrogen atoms, mercury, helium, and carbon atoms are also major sources of UV radiation. Ultraviolet radiation is divided into 3 groups based on wavelength, frequency, and energy. UVA, that's 400 to 320 nanometers. 300 to 280 nanometers. And UVC, that's 280 to 100 nanometers. UVC is the most harmful form of UV radiation. But how exactly is it harmful to humans? Our bodies function based on DNA, which instructs cells on how to work. DNA consists of complex molecules. Molecules are made of atoms, and when UV radiation enters DNA molecules, it causes electrons within the atoms to absorb energy and jump to higher energy states. This sudden change in electron position can break the bonds between atoms in the molecule, causing the structure of the molecule to collapse. This molecular collapse leads to damaged DNA. Since damaged DNA can no longer properly instruct cells, the result is malfunctioning cells. This can lead to harmful conditions such as cancer, skin burns, eye damage, and a weakened immune system. Fortunately, most UV radiation is absorbed by the ozone layer. The ozone layer contains ozone molecules, and when UV radiation strikes these molecules, it breaks them apart into dioxygen, O2, and individual oxygen atoms. This process absorbs the energy of the UV rays, preventing them from reaching Earth's surface. The individual oxygen atoms then recombine the dioxygen to form ozone molecules again. This continuous reforming cycle of ozone protects life on Earth from harmful ultraviolet radiation. X-rays X-rays have wavelengths shorter than ultraviolet waves, ranging from 10 nanometers to 0.01 nanometers, with equivalent energy levels between 12 eV and 120,000 eV. When high-energy photons strike an atom, they can eject tightly bound electrons from the atom's inner shell, ionizing the atom by causing it to lose an electron. As we know, electrons always seek to fill the inner shell, so when higher energy shell electrons fall, enter the inner shell. They release X-rays. X-rays can also be produced when high-energy, negatively charged free electrons pass near the positively charged nucleus of an atom. As the electrons are deflected by the nucleus due to the attraction between opposite charges, this sudden change in direction emits a continuous X-ray spectrum. This process is called Bremsstrahlung radiation. We produce X-rays by sudden collision of high-speed electrons. Although X-rays are more harmful than ultraviolet rays, we have developed ways to manage and use them safely. Gamma rays.
Most people spend their lives accumulating this. Erfassen lift the knowledge, weight with difficulty and knowledge. Facts. Information. They collect it, store it, hoard it, more and more, heavier and heavier. They think this weight is strength. They think accumulation is power, but it's not. It's just weight. Heavy, burdensome, difficult to carry, and mostly useless. Hey, lift the pabar, weight effortlessly. This is what scientists understand. This is what Feynman discovered. Power isn't about how much you know. It's about what you can do with what you know. How you think. How you process. How you solve. A powerful mind isn't a full mind. It's a capable mind, not storage, capability, not collection, function. A frekker put weights down, and the difference between these two, between accumulating knowledge and building power, that's everything. That's what separates people who know a lot from people who can do a lot. That's what creates capability instead of just credentials. Direct address air. Right now, you're probably building the wrong thing. You're accumulating knowledge, reading books, taking courses, collecting information, getting smarter in the way that doesn't actually matter. And you're missing the real work, the work of building a powerful mind, a mind that can solve problems, generate insights, create solutions, function at a level most people never reach. And today, I'm going to show you the scientist's method, Feynman's method, the specific practices that build power instead of just accumulation, that create capability instead of just collection. Not inspiration, not theory, but concrete, practical, actionable techniques that transform an ordinary mind into a powerful one. Because power isn't born, it's built. With a method, with specific practices, with deliberate development. Azark walk across stage. Let me start with the story that reveals the method. It's 1961. Feynman is teaching a freshman physics course at Caltech. First lecture, room full of brilliant students. Top test scores, perfect grades, the best of the best. And Feynman does something unusual. He gives them a problem, not a physics problem, a thinking problem. Share the problem. You're standing on a bathroom scale in an elevator. The elevator starts moving upward. Does the scale reading go up, down, or stay the same? Simple question, basic physics. These students have all studied physics. They all know the relevant concepts. Share the responses. Half the students say, the reading goes up because you're accelerating upward. The other half say, the reading stays the same because your mass doesn't change. Both groups are confident. Both groups use physics terminology correctly. Both groups sound like they know what they're talking about. Hair reveal the testes. Then Feynman asks a follow-up why. Explain why. What's actually happening? What forces are involved? What's the mechanism? Silence. They can't explain it. They gave answers, right or wrong, but they don't actually understand what's happening. They've memorized concepts without building thinking power. His lesson. And Feynman tells them that knowing the answer isn't power. Understanding how to figure out the answer, that's power. You have knowledge. But you don't have power. This course is going to change that. Make the distinction. That's the distinction. That's what the scientist's method builds. Not knowledge, power. Not information, capability. Not what you know, what you can do. Present the method. So what's the method? What are the specific practices that build a powerful mind? Let me show you. 6 components, 6 practices. The complete scientist's method for building mental power. Practice 1 ARS, practice 1 learn by problem solving, not by information accumulation. This is fundamental. This is where most people go wrong from the start. Most people learn by consuming information, reading, listening, watching, absorbing. They think learning is accumulation. Scientists learn by solving problems. Every concept learned through attempting to solve. Every principle discovered through wrestling with application. Hence, make it concrete's traditional approach. Read a chapter on Newton's laws. Learn FPMA. Understand the concepts. Then solve practice problems. Information first. Application second. Show the alternative. Scientists' approach. Here's a problem. Predict what happens when you push a box on ice. Try to solve it. Get stuck. Realize what you don't know. Then learn FMA specifically to solve this problem. Problem first. Learning second. Always. Faster explain why this builds power. Learning through problem solving builds power because your brain learns in context. You know not just what FMA is, but when to use it, how to apply it, what it's for. Learning through information accumulation builds collection. You know what a FMA is, but you don't know when or how or why. It's stored but not usable. Give Feynman example. Feynman never learned anything except through problem solving. Never read a chapter and then solved problems. Always tried to solve first, discovered what he needed to know, then learned that specific thing. That's why his knowledge was power. Every piece of information he had was learned in the context of use, immediately usable, not just stored. Hamar make the practice. The practice, never learn anything passively. Always start with a problem to solve. Get stuck, identify what you need to know. Learn that specifically, apply it immediately. Problem, gap, learning, application, always in that order. X, practice 2. Build models, not memories. This is critical. This separates powerful thinking from educated recall. Most people build memories. They store facts. Memorize information, create mental databases. Their mind is a library. Scientists build models. They create functional representations, mental simulations, working systems. Their mind is a laboratory. Make it concrete. How does the heart work? Memory approach. The heart has 4 chambers. The right atrium receives deoxygenated blood from the body. The right ventricle pumps it to the lungs. The left atrium receives oxygenated blood from the lungs. The left ventricle pumps it to the body. A stored information, reseatable, but not functional. Show the alternative, a model approach. Visualize a 2-pump system. Right pump handles dirty blood, sends it to cleaning station lungs. Left pump handles clean blood, sends it to body. Valves prevent backflow. Chambers allow filling and pumping in sequence. Mental simulation. Functional. You can reason with it, predict with it, apply it. Feder explain the power differences. With memories, you can recall. With models, you can think. Recall is limited. You can only remember what you've stored. Thinking is generative. You can figure out things you never explicitly learned. Give Feynman example. Feynman built models for everything. Physics wasn't equations to memorize. It was mental movies of particles interacting, fields fluctuating, forces acting. He could visualize what was happening, run mental simulations. See the mechanisms. That's why he could solve novel problems. His models let him think, not just recall. Civics make the practice. The practice for everything you learn. Build a mental model, a working representation, a functional simulation, something you can run in your mind and see what happens. Don't ask, what is this? Ask, how does this work? What would I see happening? What's the mechanism? Practice 3. Develop pattern recognition across domains. This is where power multiplies, where capability compounds, where one area of knowledge enhances all others. Most people learn domains specifically. Physics is physics. Biology is biology. Business is business. Separate. Isolated. No connections. Scientists see patterns across domains. The same principles appearing in different contexts. Universal patterns that transcend specific fields. And make it concrete. Oscillation appears everywhere. Pendulum swinging in physics. Predator-prey cycles in biology, economic boom, bust cycles in finance, population oscillations in ecology, same mathematical pattern, different contexts. If you recognize the pattern, you can transfer knowledge. Understanding oscillation in one domain gives you insight into all domains where it appears. First, show the power. This is multiplicative. Learn one pattern, gain insight into 10 different fields. Learn 10 patterns, understand 100 different phenomena. Your power isn't proportional to what you know. It's exponential, because patterns let you apply knowledge across domains. I give Feynman example. Feynman was famous for this. He'd solve biology problems using physics thinking. computer problems using quantum mechanics insights, teaching problems using scientific methods. Not because he knew everything, because he recognized patterns. Same structures appearing in different clothes. That recognition gave him power far beyond his specific knowledge. When make the practice when you learn something in one domain, ask, where else does this pattern appear? What other fields have similar structures? How is this principle universal? Build a library of patterns, not a library of facts. Patterns transfer. Facts don't. Practice. Practice 4, test your understanding through prediction. This is how scientists know they have power, not just knowledge. Through prediction. Through anticipating outcomes before they happen. Most people test understanding through recall. Can I remember this? Can I recite that? Memory tests. Scientists test understanding through prediction. Can I predict what will happen? Can I anticipate the outcome? Power tests. Make it concrete. You've learned about supply and demand. Memory test. Define supply and demand. Explain the relationship. You can pass that by memorizing. Doesn't prove power. Attack show the alternative, a power test. A new iPhone releases next week. Apple announces they manufactured fewer units than expected. What happens to prices on launch day? What happens a month later when more inventory arrives? Prediction requires understanding. Requires functional knowledge. Can't fake it with memorization. Favre explain why this matters. Prediction reveals whether your knowledge is power. If you can predict accurately, your understanding is functional. If you can't, you have stored information but not usable capability. Give Feynman example. Feynman constantly tested himself through prediction. Before doing an experiment, he'd predict the outcome. Before reading further in a paper, he'd predict what would come next. Before seeing a solution, he'd predict the approach. Right or wrong, the practice built power. Forced him to use his understanding functionally, not just store it passively. Make the practice before looking at solutions, answers, or outcomes. Predict. Use your understanding to anticipate. Right or wrong, you're building power by forcing functional use of knowledge. Make prediction a habit, constant. Automatic. Every situation is a test of whether your knowledge is power. Practice 5. Practice 5, cultivate productive confusion. This sounds wrong, but it's crucial. It's where power develops most rapidly. Most people avoid confusion. It feels bad, uncomfortable, like failure. So they seek clarity, certainty, comfort. Scientists cultivate confusion intentionally. They seek situations that confuse them, problems that perplex them, phenomena that don't make sense yet. Explain why confusion is your brain encountering the limits of its current models, the edge of its understanding, the boundary of its power. That's where growth happens. That's where power expands, not in comfort, in confusion. Make it concrete. You're learning quantum mechanics, reading about superposition. It doesn't make sense, confusing, uncomfortable. Most people push through. Try to get it, seek clearer explanations, avoid the confusion. Show the alternative. Scientists sit with the confusion. This is confusing. Why? What specifically doesn't make sense? What's my current model? Why does it fail here? What would a better model look like? The confusion is information. It reveals exactly where your understanding needs development. That's valuable. That's where power grows. Give Feynman an example. Feynman said, I can live with doubt and uncertainty. I think it's much more interesting to live not knowing than to have answers that might be wrong. He cultivated confusion, sought it, stayed in it, let it drive his learning. That's how he developed such powerful thinking, by living at the edge of his understanding instead of in the comfort of clarity. Make the practice of. The practice, when you encounter confusion, don't rush past it, examine it. What specifically confuses me? What model am I using that fails here? What would I need to understand to resolve this confusion? Confusion is the boundary of your power. Stay there. That's where power expands. Practice 6, teach to expose gaps. This is the final practice, the ultimate test and builder of power. Most people teach to share what they know, to transfer information, to explain things clearly. Scientists teach to discover what they don't know, to expose gaps, to reveal illusions of understanding. Make it concreter. You think you understand evolution. You've read about it, studied it, can discuss it. Then you try to teach it to someone who knows nothing, and you get stuck. Realize you can't explain certain parts. Don't understand specific mechanisms. Have gaps in your model. Show the value. Teaching exposes those gaps, reveals illusions, shows where your power is real and where it's imagined. And that revelation is valuable. Now you know exactly what to learn, where to develop, how to build real power instead of just collecting information. As our Richard Feynman example, Feynman's famous technique explain a concept to someone who knows nothing using simple words. Where you get stuck, where you need jargon, where you can't simplify, those are your gaps, not a teaching technique, a power-building technique, a method for discovering and filling gaps in your understanding. Make the practice. The practice regularly teach what you're learning, to friends, to family, to imaginary people out loud with no jargon. Where you struggle, you found gaps. Fill those gaps specifically. Teach again. Repeat until smooth. Each cycle builds power, real power, functional capability. Hey heck, bring method together ether. So that's the complete method. 6 practices that build a powerful mind. 1. Learn by problem solving, not information accumulation. 2. Build models, not memories. 3. Develop pattern recognition across domains. 4. Test through prediction. 5. Cultivate productive confusion. 6. Teach to expose gaps. Make the promise. Use these 6 practices consistently, and you build a powerful mind, not just a full mind, a capable mind. Power, not just knowledge. Fair tell transformation story. Let me tell you about someone who applied this method. Call him David. David was a software engineer. Good education, CS degree, years of experience, knew a lot about programming, lots of knowledge, but limited power, could build what he'd built before. Struggled with novel problems, couldn't transfer knowledge across languages or frameworks. His knowledge didn't translate to power. The discoveries. Then he learned the scientist's method. 6 practices for building power, and he decided to apply them systematically. His implementation ends. Practice 1 stopped reading tutorials. Started with problems. I want to build this thing. Try to build it. Get stuck. Learn what I need specifically to solve the blockage. Problem-driven learning. Every piece of knowledge acquired in context of use. Continue. Practice 2 built mental models of how systems work. Not memorizing syntax. Visualizing what code does. Running mental simulations of execution. Functional understanding. Practice 3 recognize patterns. This is just a state machine. I've seen that in embedded systems and game AI. Same pattern, different context. Transferred knowledge across domains. Effects and continui. Practice 4 predicted outcomes before running code. If I write this, what should happen? Test through prediction. Build power through anticipation. Practice 5 cultivated confusion. When something didn't make sense, sat with it. Examined it. Why is this confusing? What's my model? How does it fail? Let confusion drive deeper understanding. Continue. Practice 6 taught constantly to junior developers, to non-programmers, to himself out loud, exposed gaps, filled them, built real power. Of the transformation 6 months different developer. Not just better at what he knew, capable with what he didn't know, could tackle novel problems, transfer across domains, generate solutions. 2 years, senior position, leading complex projects. Not because he knew more languages or frameworks, because he had power, real capability. Make the universal point. That's what the method builds. That's what these practices create. Not collection. Capability, not storage. Power. Avase address the deeper principle that here's the deeper principle that makes this method work. Your mind isn't a container. It's a processor. Its power isn't determined by how much it holds. It's determined by what it can do. Make the analogy of think of computers. You can have a computer with a terabyte hard drive and a weak processor. Lots of storage, little power. Can store massive amounts of data but can barely run programs. Or you can have a computer with a small hard drive and a powerful processor. Limited storage, enormous power, can run complex programs, solve difficult problems, generate solutions. As I apply to minds first, most people build the first kind, big storage. Weak processing. They accumulate knowledge but don't develop capability. The scientist method builds the second kind, sufficient storage, powerful processing, capability to solve, create, generate, think. Make the choice clear. So what do you want to build? A mind that knows a lot or a mind that can do a lot? The answer determines your approach, determines whether you accumulate or develop, collect or build. That present the mindset shift. This requires a mindset shift, a fundamental change in how you think about learning and intelligence. Shift 1 from what do I know to what can I do? Stop measuring yourself by information accumulated. Start measuring by problems solved, capabilities developed, functions mastered. EC Shift 2. From how much have I learned to how powerful is my thinking. Stop counting books, read courses taken, facts memorized. Start assessing thinking capability, problem solving power, functional ability. A Shift 3, Shift 3. From I need to know this to I need to be able to do this. Stop asking, what should I know? Start asking, what should I be able to do? What capability do I need? What power am I building toward? Heck, make these shifts concrete. These aren't semantic. These fundamentally change your approach to learning and development. What do I know? Leads to accumulation. What can I do? Leads to power. How much learned? Leads to collection. How powerful is my thinking? Leads to capability. I need to know this. Leads to storage. I need to be able to do this. Leads to function. Ayers share the implementation. So how do you implement this method? How do you actually build a powerful mind starting today? Give the plan week 1, start with practice 1. Learn something through problem solving. No passive reading. Pick a problem you want to solve. Try to solve it. Learn what you need as you need it. Week 2, add practice 2. As you learn, build mental models. Visualize mechanisms, create functional representations. Not what is it called, but how does it work? Week 3, add practice 3. Look for patterns. What you're learning. Where else does this appear? What's universal about this structure? Continue week 4, add practice 4. Start predicting. Before seeing solutions, predict what will happen. Test your understanding through anticipation. Week 5, add practice 5. When confused, examine the confusion. Don't rush past it. Let it reveal where you need development. Week 6, add practice 6. Teach what you're learning. Expose your gaps. Fill them. Build real power. Hours, make the time frame of 6 weeks to implement all 6 practices. Then maintain them. Make them habits. Your default approach to learning and thinking. Act, promise the result. 6 months of this method, measurably more powerful thinking. Can solve problems you couldn't before. Understand concepts that were opaque before. Generate insights that were impossible before. 1 year. Unrecognizable capability. Your thinking power has multiplied. Your ability to solve, create, understand has expanded dramatically. S are walk to center S. So here's what you need to understand. Most people are building the wrong thing. They're accumulating knowledge, collecting information, getting educated. But education isn't power. Collection isn't capability. Knowledge isn't the same as a powerful mind. Facts direct statement error. A powerful mind is built through specific practices. The scientist's method. 6 deliberate approaches that develop capability, not just accumulation. Repeat the method. Learn through problem solving. Build models, not memories. Recognize patterns across domains. Test through prediction. Cultivate productive confusion. Teach to expose gaps. Act the promise. Use this method consistently, and you build real power. Thinking capability that multiplies over time. Problem-solving ability that compounds. Understanding that generates insight, not by knowing more, by being able to do more with what you know. Final challenge. So here's my challenge. Pick one capability you want to develop. One thing you want to be able to do. Not one thing you want to know. One thing you want to do. And build that capability using the scientist's method. Start with a problem that requires that capability. Try to solve it, get stuck. Learn what you need. Build models. Recognize patterns. Predict outcomes. Sit with confusion. Teach it. Make the prediction. Do this, and you'll discover something profound. Power doesn't come from accumulation. Power comes from development, from building capability systematically through practice. A final statement: you don't need more knowledge. You need a more powerful mind, and a powerful mind isn't born, it's built, with a method, with practices, with deliberate development. But pauses. That's the scientist's method. That's how Feynman built his extraordinary thinking capability. That's how you can build yours. Not by collecting more, by developing power. Thank you. Inten, if you want detailed techniques for each of these 6 practices, if you want specific exercises for problem solving, learning, model building, pattern recognition, prediction testing, productive confusion, and teaching to expose gaps, do me a favor, like this video and subscribe to the Mind of Richard Feynman channel. We're exploring how to build real thinking power, how to develop capability, not just accumulate information, how to create a powerful mind. Join us. Let's build power together. See you in the next one.
People love answers. simple ones, clean ones. Is light a wave or a particle? And they want the experiment to pick a side, like a referee blowing a whistle. That demand is the first mistake, because nature is not obligated to satisfy our categories. Consider the famous setup. Light passes through two narrow slits and forms an interference pattern, a result that screams wave, fine. Then we dim the source until light arrives one tiny flash at a time. Now each event lands at a single point, like a particle. Yet over time, the same interference pattern quietly reappears. So people ask, aha, is this the proof? Have we finally caught light pretending to be a particle? No. That conclusion is lazy. What the experiment actually shows is far more disturbing. Each individual detection behaves like a localized event. Yes, but the distribution of those events follows a rule that no classical particle could ever obey. The pattern is not drawn by particles bumping into each other. It is drawn by probability amplitudes interfering with themselves. And here is the trap. The moment you try to observe which slit the light goes through, the moment you insist on a particle story, the interference vanishes. Not because light decided to behave differently, but because the question you asked destroyed the conditions required for interference. This is not proof that light is a particle. It is proof that asking particle-type questions forces particle-type answers. The experiment doesn't reveal the true nature of light. It exposes the limits of the questions we are allowed to ask. If light were really a classical particle, it would choose a slit and the pattern would disappear even when unobserved. If it were really a classical wave, energy would smear continuously across the screen instead of arriving in discrete hits. But it does neither. The experiment refuses to cooperate with our intuition. So what does it prove? It proves that nature does not operate in terms of pictures we can visualize, only in terms of mathematical rules that predict outcomes. And those rules work perfectly, whether we like them or not. The failure is not in the experiment. The failure is in our insistence on asking, which one is it? The correct answer is brutal and unsatisfying. Light is not a particle. Light is not a wave. Light is whatever obeys these rules, and nothing more needs to be added. If that makes you uncomfortable, good. That discomfort is the sound of understanding beginning, because the moment you stop demanding a simple picture is the moment the experiment finally makes sense. An experiment never proves a philosophy. That single sentence already offends the way most people want science to work, and that's exactly why it matters. We are trained, almost conditioned, to believe that an experiment delivers truth in a clean package, stamped and sealed, ready to be believed forever. But experiments don't operate at that level. They don't certify worldviews. They don't settle metaphysical arguments. They answer narrow, sharply defined questions about what happens when nature is cornered under specific conditions. The moment you ask an experiment to do more than that, you've already stepped outside science and into storytelling. A philosophy is a way of thinking about reality. An experiment is a way of interrogating behavior. Confusing the two is how people end up declaring victory in debates that science was never trying to win. When someone says this experiment proves that reality is this way, what they usually mean is this experiment makes me comfortable with one interpretation over another. Comfort is not evidence. Nature doesn't care what we find intuitive, elegant, or emotionally satisfying. Take any famous experiment you like. Strip away the mythology, the diagrams in textbooks, the dramatic narration. What's left is a set of conditions, a set of measurements, and a pattern in the data. That's it. The experiment does not speak in sentences. It does not whisper philosophical truths. It simply behaves. We are the ones who translate that behavior into stories, and stories always carry assumptions. The danger begins when we forget that translation step exists. When people claim that an experiment proves a deep philosophical claim, they are smuggling in extra ideas that were never measured. They're taking a result that says, under these conditions, this is what we observe, and inflating it into, this is what reality fundamentally is. That jump feels small, but it's enormous. It's the difference between describing a phenomenon and declaring the nature of existence. Experiments are brutally honest, but also brutally limited. They answer only the question you asked, and sometimes not even the question you thought you asked. If your experimental setup assumes a certain framework, your results will obediently live inside that framework. That's not bias in the moral sense, it's structural. You cannot design an experiment without assumptions. You can only design one that makes them explicit or hides them so well you forget they're there. This is why experiments don't settle philosophical debates, they constrain them. They narrow the range of stories you're allowed to tell. They eliminate bad explanations. They expose contradictions. But they never hand you the final narrative. Anyone claiming otherwise is mistaking precision for depth. Think about how often people say, "Science has proven that." Proven what exactly? A measurement? A correlation? A statistical pattern? Fine. But when that sentence ends with a claim about meaning, purpose, or ultimate reality, something has gone wrong. The experiment didn't cross that bridge. You did. This misunderstanding is especially seductive in areas where intuition fails. When results defy common sense, people panic. They rush to label the outcome in familiar terms as if naming it restores control. Particle, wave, deterministic, random. These labels feel like understanding, but they are often just intellectual comfort blankets. The experiment never demanded them. We did. An honest experiment is silent on interpretation. It doesn't tell you what is, it tells you what happens. The rest is negotiation between theory, mathematics, and human imagination. That negotiation is where philosophy sneaks back in, whether we admit it or not. And here's the uncomfortable part. Two people can fully agree on the experimental results and still disagree completely on what they mean. That alone should tell you something. If an experiment truly proved a philosophy, disagreement would end where the data ends. But it never does. The arguments continue, refined, sharpened, sometimes more heated than before. Not because the data is unclear, but because philosophy was never on trial in the first place. The strength of science is not that it answers ultimate questions. Its strength is that it refuses to. It builds models that work, predictions that succeed, and technologies that function without demanding a final picture of reality. That restraint is not a weakness, it's discipline. The moment science starts declaring what reality must be, it stops being science and starts behaving like doctrine. So when you hear that an experiment has proven a philosophy, pause. Ask what was actually measured. Ask what assumptions were built into the setup. Ask what alternatives were ruled out and which ones quietly survived. You'll usually find that the experiment did something far more interesting than proving a belief. It exposed how fragile our beliefs are when nature refuses to play along. An experiment never proves a philosophy because philosophy is not something you can measure, isolate, or put on a detector. What an experiment can do, when used properly, is far more powerful. It can force philosophy to shut up for a moment, sit down, and rewrite itself under stricter rules. And that, whether people like it or not, is the real lesson hiding behind every great experiment. Light is not confused. That accusation belongs entirely to us. When people say that light sometimes behaves like a wave and sometimes like a particle, what they are really admitting is not a flaw in light, but a failure in the way we insist on understanding it. Nature is doing something perfectly consistent, following rules with absolute discipline. The confusion arises only when we try to force those rules into mental pictures that were never designed to handle them. We approach light carrying intellectual baggage from everyday experience. In our world, objects are either things or motions. A stone is a thing, a ripple on water is a motion. We learn early that these categories do not mix. So when we meet a phenomenon that refuses to stay in one box, we blame the phenomenon instead of questioning the boxes. Light does not hesitate. It does not switch personalities mid-experiment. It does not decide how to behave based on our expectations. It does exactly what it always does. The only thing that changes is the question we ask and the way we try to describe the answer. The moment we call light a particle, we are importing assumptions that come from macroscopic objects, definite position, a continuous path, a trajectory that exists whether we look or not. The moment we call it a wave, we import a different set of assumptions, spread out influence, interference, smooth continuity. These ideas work beautifully in the domains where they were born. They fail the instant we demand that one of them explain everything light does. What experiments reveal is not indecision, but discipline. Each setup produces results that obey precise mathematical rules. Those rules never wobble. The probabilities line up exactly as predicted. The patterns appear exactly where they must. If light were truly confused, experiments would be messy, inconsistent, unreliable. They are not. They are so consistent that we can build technologies with absurd precision using them. The confusion cannot be in the phenomenon. It has to be in the story we tell ourselves about it. Our discomfort comes from wanting a picture. We crave something we can visualize, something that moves through space the way objects in our daily lives do. But visualization is not a requirement of reality. It is a psychological preference. Nature does not owe us a mental image that fits inside our evolved intuitions. When we demand, we end up with paradoxes that feel profound, but are often self-inflicted. Light does not contradict itself. Our descriptions do. We switch languages depending on the outcome we want to explain, then act surprised when the languages don't agree. That is not evidence of a mysterious identity crisis in light. It is evidence that our classical concepts were never meant to survive this regime intact. They are approximations, useful in limited contexts, and misleading when treated as universal truths. The real mistake is thinking that reality must correspond to a single familiar category. When that expectation fails, we label the failure as weirdness in nature rather than recognizing it as a limitation of our thinking. Light obeys a set of rules that can be written down, tested, and used to make astonishingly accurate predictions. Those rules do not mention particles or waves as fundamental objects. Those words are crutches we use to talk to each other, not instructions that nature follows. Once this is understood, many apparent mysteries lose their drama. There is no need to imagine light choosing how to behave. There is no need to picture it as secretly knowing whether we are watching. These ideas are attempts to rescue intuition after it has already been defeated. The rules work without them. The outcomes appear without hesitation. The mathematics runs silently underneath, indifferent to whether we find it satisfying. What unsettles people is not that light seeks clarity, but that clarity exists at a level that resists storytelling. We want causes we can point to and paths we can trace. Instead, we are given relationships between possible outcomes, expressed with ruthless precision and zero regard for how they feel. That is not confusion. That is honesty. When we stop accusing light of being strange and start admitting that our expectations are, something important happens. We stop asking it to fit our metaphors and start listening to what experiments actually say. And what they say, again and again, is that nature operates consistently, predictably, and without apology, even when our favorite ideas fail to keep up. Light is not confused. It never was. The only confusion lies in our refusal to accept that understanding does not always come with a picture, and that reality can be perfectly well defined even when it refuses to look familiar. The double-slit experiment is not about particles versus waves. That framing is already a distraction, a comforting story we tell ourselves to avoid facing what the experiment actually forces us to confront. The moment the discussion collapses into a debate over labels, the most important lesson has already been missed. The experiment does not exist to help us choose between two familiar categories. It exists to show us that those categories are insufficient. At first glance, the setup looks innocent. Two narrow openings, a source, a screen. When both slits are open, an interference pattern appears. Close one slit, and the pattern changes. This tempts us to reach for a wave explanation because waves interfere. Then we reduce the intensity until detections occur one at a time, and suddenly each event looks localized. That tempts us to reach for a particle explanation because particles arrive in discrete hits. And there, right in that oscillation between explanations, is where people think the mystery lies. But that is not the mystery. That is the misdirection. The experiment is not asking what is light really made of. It is asking a far sharper question. Under what conditions are certain predictions valid, and under what conditions do they fail? The results are not contradictory. Our expectations are. We are trying to force a single classical narrative to survive in a domain where no such narrative applies universally. What the experiment actually reveals is that the outcome depends on the structure of the information available, not on a hidden identity crisis inside the phenomenon. When no attempt is made to determine which path is taken, the statistical pattern reflects interference, When path information is introduced, the interference disappears. Not because something physically dramatic happens at the slit, but because the rules governing the predictions have changed. This is the part that people resist. They want to believe the experiment is exposing some secret behavior happening behind the scenes, as if the system is flipping between modes. But the mathematics never describe such a flip. There is no instruction that says, now behave like a wave, followed by, now behave like a particle. There are only rules for calculating probabilities based on what is physically allowed to be known. The double-slit experiment is about limits. Limits on description, limits on prediction, and limits on the kinds of questions that have meaningful answers. When you ask a question that requires distinguishing paths, the interference terms vanish from the calculation. When you don't, they remain. This is not philosophy smuggled into physics. It is operational fact. The experiment does not reward curiosity indiscriminately. It punishes certain questions by making their answers incompatible with other phenomena. The insistence on particles versus waves comes from a desire for ontological comfort. We want to know what something really is when nobody is looking. But the experiment never provides that information. It provides correlations between preparation, measurement, and outcome. Anything beyond that is an interpretation layered on top of the data. What makes the double-slit experiment unsettling is not that it mixes particle-like and wave-like behavior, but that it refuses to give a single picture that survives every context. The experiment does not collapse under this refusal. Our intuition does. The predictions remain flawless. The results remain reproducible. The discomfort is psychological, not scientific. If the experiment we read truly about particles versus waves, then settling the question would resolve the tension. But it never does. No matter which side you pick, something breaks. Treat it as a particle, and you lose the pattern. Treat it as a wave, and you lose the discreteness of detection. The failure is not in the experiment, it is in the demand for exclusivity. What the double-slit experiment really teaches is that nature does not organize itself around the categories we find familiar. It organizes itself around rules that connect possibilities to outcomes, and those rules do not care whether we find them intuitive. The experiment is not a referendum on the nature of light. It is a warning about the limits of classical thinking. Once that is understood, the argument dissolves. The experiment stops being a battlefield between metaphors and becomes what it always was, a precise demonstration that the world is not obligated to fit into the concepts that worked at human scales. The double-slit experiment is not about particles versus waves. It is about learning when a question is meaningful, and when it quietly destroys the very phenomenon it seeks to explain. Measurement is not passive. The moment you try to treat it as a neutral act, something that merely reveals what was already there, you have already misunderstood what is happening. Measurement is not a pair of eyes quietly observing the world from a distance. It is an interaction, a physical process that alters the situation in a precise and unavoidable way. Pretending otherwise is comforting, but it is wrong. In everyday life, measurement feels harmless. You look at a thermometer, and the temperature seems unchanged by the act of looking. You weigh an object, and it still exists afterward in essentially the same state. These experiences train us to believe that measurement is a window onto reality, not a hand reaching into it. That belief works well at human scales, where disturbances are small and easily ignored, but mistaking convenience for principle becomes a serious problem the moment we step outside that domain. At fundamental scales, measurement cannot be separated from interaction. To measure anything, something must happen. Energy must be exchanged. Information must be transferred. A device must couple to what is being measured. There is no such thing as a measurement without consequence. The only question is whether the consequence is negligible or decisive. At small scales, it is decisive. The illusion of passivity survives because we imagine properties as pre-existing facts, waiting patiently to be read off. We picture position, momentum, or path as labels already attached to a system, and measurement as the act of reading the label. But this picture collapses the moment experiments demand more precision. The act of measurement does not simply reveal a property, it helps define which properties can meaningfully exist in that context. This is not a mystical claim, it is a practical one. When you design an apparatus to measure a particular quantity, you are not just choosing what to observe, you are choosing which aspects of the system will be sharpened and which will be blurred. The structure of the measurement determines the structure of the outcome. That is not because reality is vague, but because certain combinations of properties cannot be simultaneously well defined under the same physical interaction. The resistance to this idea often comes from the fear that it undermines objectivity. If measurement changes what is measured, people worry that science becomes subjective. But the opposite is true. Measurement is objective precisely because its effects are lawful, predictable, and reproducible. The disturbance is not arbitrary. It follows strict rules. Anyone using the same setup will produce the same statistical results. There is no personal element hiding in the process. What fails is the fantasy of a detached observer. The world does not offer a vantage point from outside itself. Every attempt to extract information requires participation. Measurement is not an act of watching, it is an act of doing. The outcome reflects that fact with ruthless consistency. The real lesson is not that reality depends on observers, but that it depends on interactions. The observer matters only insofar as they choose how the interaction is arranged. Once that choice is made, the result is no longer up for negotiation. Nature responds exactly as the rules demand, without concert, for whether we find the answer satisfying. When this is ignored, people invent unnecessary paradoxes. They imagine that systems behave one way when watched and another when ignored, as if awareness itself were the cause. That is a mistake born from sloppy language. What matters is not awareness but coupling. Change the coupling, and you change the outcome. Remove it, and different possibilities remain available. No consciousness is required. Measurement is not passive because it cannot be. Information does not flow for free. To learn something about a system is to leave a mark on it, however small. At macroscopic scales, that mark can be ignored. At fundamental scales, it cannot. The laws do not bend to preserve our intuitions about observation. Our intuitions must bend to match the laws. Once this is accepted, the mystery softens. There is no betrayal of realism, no collapse into subjectivity. There is only a recognition that knowledge has a physical price. Measurement pays that price every time it is performed, and the universe, indifferent and precise, keeps perfect track of the transaction. If you think you understand the result intuitively, you are misunderstanding it. That sentence sounds arrogant until you realize it is a warning, not an insult. It is not saying that understanding is impossible. It is saying that the kind of understanding you are reaching for is the wrong one. Intuition is built from everyday experience, and everyday experience is shaped by a world. D that is slow, large, and forgiving. The result you are trying to understand does not live in that world. When intuition feels satisfied too quickly, it is usually because it has quietly replaced the phenomenon with a familiar story. Intuition works by analogy. It asks, what does this remind me of? And then borrows meaning from something already known. This is powerful when the new situation genuinely resembles the old one. It is disastrous when it does not. At fundamental levels, the universe does not resemble our daily environment in any deep way. The rules are different, the constraints are different, and the questions that make sense are different. Intuition does not adapt fast enough to handle this, so it cheats. It forces the result into a picture that feels comfortable and then declares victory. That false victory is the misunderstanding. When people say they get it intuitively, what they usually mean is that they have found a mental image that stops the discomfort. The image may involve little objects taking paths, or ripples spreading through space, or hidden processes operating behind the scenes. The problem is not that these images are crude. It is that they smuggle in assumptions the result does not support. The intuition feels good because it restores a classical sense of cause and effect, but the price is accuracy. The most dangerous misunderstandings are the ones that feel clear. Confusion at least signals that something is unresolved. Intuitive clarity in the wrong domain signals that the mind has stopped asking hard questions. The result has been domesticated. Its sharp edges have been filed down until it fits inside a familiar box. At that point, learning has ended. Real understanding at this level does not feel intuitive. It feels constrained. It feels like accepting rules that work without asking whether they match your mental pictures. You stop trying to imagine what is really happening and start focusing on what can be predicted, calculated, and tested. This feels unsatisfying at first because it denies the kind of understanding we are used to, but it is honest. The insistence on intuition often comes from a hidden belief that reality must be understandable in human terms to be legitimate. That belief is not scientific, it is emotional. It confuses accessibility with truth. The universe is under no obligation to align itself with the cognitive tools that evolve for survival on a warm rock at moderate speeds. When a result violates intuition, the correct response is not to fix the result, but to interrogate the intuition. Ask where it came from. Ask what assumptions it relies on. Ask which experiences trained it. You will almost always find that intuition is extrapolating far beyond its jurisdiction. It is using rules learned in one regime and applying them where they know longer hold. This does not mean that understanding is purely abstract or meaningless. It means that understanding takes a different form. Instead of pictures, you get relationships. Instead of stories, you get structure. You understand by knowing what follows from what can be said together, and what cannot. This kind of understanding is quieter and less emotionally satisfying, but it is far more reliable. The irony is that people often reject this deeper understanding because it feels incomplete. They want to know what is really going on. But that demand assumes there is a single coherent narrative behind the result that can be told in everyday language. Sometimes there isn't. Sometimes the closest thing to what's really going on is a set of rules that refuse to collapse into a story. When intuition finally breaks, many people interpret that as a failure of explanation. In reality, it is a success. It means you have reached a boundary where familiar thinking stops working. That boundary is not an obstacle. It is the point of the exercise. Crossing it requires discipline, not imagination. If you think you understand the result intuitively, you are misunderstanding it. Because true understanding here does not feel like recognition. It feels like submission to constraint. It feels like accepting that the universe will not explain itself on your terms. And that acceptance is not a loss. It is the moment you stop demanding comfort and start demanding correctness.